in a composition, when the outside function involves an exponent, then the power rule applies, of course. And the power rule says that the exponent comes out front as a coefficient, and then we subtract 1 from the exponent. And then if the base function is not just plain x, then the chain rule applies. And so we would have that power rule times f prime in this case, the derivative of the inside function. That's known as the general power rule, and let's just see it in action. It's nothing more than the chain rule. Apply it in particular to a power function. We have here differentiate f of x is equal to the quantity of 1 plus x squared, whole thing to the 99th power. So we've got f prime of x is equal to 99 times the quantity of 1 plus x squared to the 98th power times the derivative of the inside function, which is 1 plus 2x. I know, it's not big and fancy. There's just a name for this, the general power rule. And it's going to apply in the next example. U of y is equal to y to the 4th plus 1 over y to the squared plus 1, whole thing to the 5th power. Looking at this as general structures, what I have in on the outside is a power rule. So that's going to be u prime of y is equal to 5 times the thing in parentheses to the 4th power. But then we have times the derivative of the thing in the parentheses. Now that is a quotient. What I'd like you to do at this point is, I want you to pause the video and finish this, but here's the deal. I want you to simplify as much as possible. All right, in the fraction, I have u is y to the 4th plus 1 and v is y squared plus 1. You may think, but u is our function. How am I able to use u and v? Well, I'm using lowercase u and v over here, and that's different from uppercase u, I know. And I use the quotient rule, which is u prime v minus uv prime over v squared. And in the denominator here, I have a y squared plus 1, which is ultimately to the 4th power. And here I have a y squared plus 1, the quantity squared. So that is, they combine to the 6th power. That's kind of the simplifying that I meant. And then in the numerator of, the chain rule part, I have terms that combine, right? So I have 2y to the 5th plus 4y cubed minus 2y. If you left it like that and put it in parentheses and made it in, put it in the numerator, then that's fine. But I went ahead and decided to factor out the 2y and combine that with the 5. So I have 10y times the quantity of y to the 4th plus 1. Oh my gosh, that's to the 4th power. I'm glad I caught that. 4th power applied to both the numerator and denominator. Times y to the 4th plus 2y squared minus 1 all over y squared plus 1 to the 6th power. One thing that came up when I was doing my work over here is I made my v over here look like a u. And this is something that I forgot to mention in a previous video. When you're using the product rule or the quotient rule, sometimes people have like a u and a v that look like each other. I recommend that you don't do that when you're writing math. Make sure that your u looks different from your v. It may not be a big deal to you, or it may not seem like a big deal to you, but it kind of is. And down the road, it'll be kind of a problem if you're not able to distinguish your u from your v. Maybe in this class, maybe in the next class, but it would be good to distinguish the symbols that you're using. Now we're going to use the general power rule to prove that the derivative with respect to x of the secant of x is equal to the secant of x times the tangent of x. And we're going to do this by considering that the secant of x is equal to the reciprocal of the cosine of x. And for this, I'm going to write it down as the cosine of x to the -1. Not the inverse cosine of x. That's not what I'm talking about. I'm talking about the reciprocal. Cosine of x to the -1. So the derivative with respect to x of the cosine of x to the -1 is going to use the general power rule, which means I'm going to pull a negative out front, or -1 out front if you like. Cosine of x to the -2 power. So that's the power rule. But then I need to bring in the chain rule, and the derivative of the cosine is the negative sine. So I have times negative sine of x. Negative times negative is going to give me positive, and I have sine of x times 1 over the cosine squared of x. I'm going to take one factor of cosine and put it underneath the sine function, and that's where my tangent of x is going to come from. And I have one remaining factor of cosine of x in the denominator. That's going to be our secant of x. And there's the derivative formula for the secant function.